Hello, my name's Stuart and I'll be giving you an introduction to live video processing with OpenCV. If you haven't discovered OpenCV before, it's a fantastic open source library for image processing, machine learning and computer vision. It's cross-platform. It runs on desktop, mobile devices, servers, and even on some hardware and small computers like the Raspberry Pi. It comes with a variety of language bindings, so C++, Python, Java, they're out of the box. There's also bindings for C# and many other programming languages. And it's also very fast. It'll take full advantage of vectorized CPU instructions such as SSE and AVX. If you've got more than one core in your system, it'll take advantage of that. And it has a very easy and straightforward way to take advantage of GPUs. And today I'm spoiled because I've got a Blackmagic eGPU connected, and we'll see just how much of a speed up that gives us. So what we're going to do in this demonstration is we're going to be capturing live video from camera 2, the one I'm looking at now. It'll be captured in a DeckLink device. Now on the desk here I've got a DeckLink 4K Extreme PCI DeckLink device. There's a range of other DeckLink devices, but the one I'll be processing today with is this Ultra Studio 4K Extreme. So we've got the camera 1 going into the input of that. We're going to be processing it and then composing a new frame and outputting that over the Ultra Studio as well. Now in the diagram there, we've got a video frame coming in, and the DeckLink device will capture it and call our video input frame arrived function. Then we're going to do some processing steps, compose an output frame and schedule that for play out. Now because we've spent time processing, there's always going to be at least one frame of delay before you can play it out. Now the scenario that we're kind of representing here is you're at a technical conference, you've got a lot of detailed information being displayed on screen, and you've got a presenter who's standing on a stage, perhaps walking up and down, pointing to the screen. You may not be able to have a dedicated cameraman who can frame the shot and keep the presenter in the center of the shot, but by using say a 4K camera fixed to the stage, framed on the stage, you could then track the person's face, extract their face, put it in the top left corner of your composed output, and have a very pleasing and engaging presentation. So the face detection algorithm that we're going to be using is the HAR cascade classifier, and this is built up of weak classifiers. So an example of a weak classifier is an edge, which is going from dark to light. Another classifier would be a line, so that goes from dark to light to dark. So on the face, these weak classifiers match quite well. So the line classifier would go from a light of the forehead to a darker line of the eyebrows, and then the line classifier would match nicely, going from the dark of an eye to the bridge of the nose and the dark of the eye again. These classifiers are grouped into stages. So on the first pass, the entire image is processed using a weak classifier, and it will only match in certain parts of the image. In the next stage, it will be able to eliminate the areas that didn't match the first stage and apply more classifiers to those, and so on, until you get many classifiers being run, and you reduce the amount of computing time substantially by arranging them into this cascade. At the end of the cascade, you'll end up with quite an accurate algorithm for detecting faces. So let's jump into some code now and have a look at what we need to do. So in my DeckLink device that's running here, I need to enable the input and the output. And then I start the scheduled playback and I start the streams. So this is enough to get loop through going through. So on the Ultra Studio output, I'll just enable that now. So we've got live loop through capturing from camera 2 going through to the output of the Ultra Studio. And the next step I do is I set up the face detection. So this is the first time we use an OpenCV call. So we construct the OpenCV cascade classifier, and I'm going to initialize it with the frontal face detector. Now, because I'll be looking directly at camera 2, we're going to be using the frontal face detector, but there's other detectors there. There's a upper body detector, which would be more suitable if you've got a presenter walking up and down a stage. There's also full body detectors, smile detectors, eye detectors, and there's even a cat face detector. And I've tried that out, and it's very good at discriminating human faces from cat faces. So when we capture a frame, the DetectLink SDK will call our video input frame arrived function. And the first thing we do is get a pointer to the data with getBytes. And then, depending on the source, we may need to do a color space conversion. So here I'm capturing from an SDI camera, so the output of that is YCBCR or YUV. That's very straightforward. But if you're capturing from a gaming console over an HDMI cable, that's almost certainly going to be RGB. And so there you can call the DetectLink function convert frame, and that will convert that to YUV. And then we can call the OpenCV convert color. So OpenCV doesn't convert all formats to all other formats, but the DetectLink SDK has convert frame, which will handle, in many cases, some of the formats that you'll be dealing with in practice. So we've got our frame that we're processing. We convert it to grayscale, and then we run the DetectMultiscale. So that is the face detection algorithm being run. And the first thing you want to do is see, well, how long does it take to process one frame of 4K video? Now that took 25,000 milliseconds. So if we're going to do 60 frames a second, we have a goal there of 16.6 milliseconds. So 25 seconds, 16.6 milliseconds, it's just not going to work. We're going to have to speed it up somehow. Now, one obvious way to reduce the amount of data that must be processed is to scale down that 4K image. And here I'm going to scale it down by a factor of 8 in both the X and the Y directions. So overall, I'm going to have an image that's 1/64th the size of the original 4K frame. After running DetectMultiscale, that takes 18 milliseconds. So that's a lot better. Now I'll just show you the output of the grayscale step here. So that's the original 4K image in grayscale. I'm going to show what it looks like after scaling it down, and then I obviously need to scale it back up to 4K for the purpose of this demonstration. So you can see the image is a lot softer. Now if I scale down, I think by a factor of 32 in both directions, it looks terrible, and the face detection doesn't have enough information there to find a face. Now if I was running the upper body detector, it probably would be able to find the upper body there. There's enough information. So we'll go back to the scaling down. Now another thing to note when scaling down is you need to use the right filter. So if you use the naive nearest neighbor filter, you'll end up with quite a noisy image. So you can see there's lots of artifacts there. Any little bit of movement makes those artifacts even more obvious. So we'll go back to grayscale, and we'll look at other ways we can speed it up, because 18 milliseconds is not quite at our minimum goal of 16 milliseconds per frame. So one thing I thought I would do is write a custom loop. In that previous step, I was doing the convert color and the resize as two separate steps. Here, I wrote a loop to do it all in one go. So I'm looping over each row and each column in the image, and I'm pulling out just a green value, which I'm going to treat as my grayscale value. So every 8th row, every 8th column, and the green value. So a very simple, naive way to downsize and convert the color. When I ran DetectMultiscale after that, I was surprised to see that the time went up, 40 milliseconds. Now that's because with OpenCV, in its convert color and its resize functions, even though they were two different steps, it's taking advantage of all those SSE and vectorized CPU instructions. It's taking advantage of the multi-cores in this Mac and doing all of that behind the scenes. When I went ahead and did those two steps in one, although I was probably having better memory access, just iterating over the memory once, I wasn't taking advantage of AVX and SSE instructions or the cores. So that's why my naive custom loop was slower. So we're only still at 18 milliseconds. We need to now go a little bit further. And I'm a little bit spoiled here. I've got an eGPU connected, so I can try to take advantage of that. Now, in the older version of OpenCV, OpenCV 2, and in other libraries, it's a lot of work. You've got to write your own CUDA or OpenCL kernel. You've got to upload that to the GPU. You've got to manage the execution pipeline, download the data at the end. It's a lot of work, and a lot of software developers would simply skip it. It's too hard, too much work. With OpenCV 3, it's introduced a new data type called UMAT, which is just like its basic built-in MAT, but it'll take advantage of the GPU behind the scenes for you. So the U in UMAT stands for universal, and that means it takes advantage of all and any hardware accelerations that are available. So let's take a look at what's changed now in our code. So in that second line, we've got UMAT. So that's our output image, our image that we're processing. The original image is still a MAT. And that first step, convert color, that will take the input pixels, it'll upload them to the GPU because the output image type is a UMAT, and it'll do the color space conversion on the GPU. Then we'll go to do the next step, the resize. Its input parameter image is already a UMAT, and that's already on the GPU, and the output image is also on the GPU, so that will be processed entirely on the GPU. And then when we go ahead and run DetectMultiscale, that image object is also has a lot of its data on the GPU, so a lot of the steps of the DetectMultiscale algorithm, which is doing many thousands of rectangle operations, will be substantially faster. And when we look at the total time, 8 milliseconds. So now we're well within our, if you like, time budget of 16.6 milliseconds. So we've got spare time to do something with the detection. And in the next steps, I'll show you what we're going to do. First, just a little aside about using UMAT. Because it doesn't represent memory that's available to the CPU, there's a couple of traps that you might fall into. So in the first line, we've got MAT, which is the image CPU. That's got a data pointer in its constructor that points to CPU memory. That's OK. If we construct on the second line image UMAT, which is a UMAT, it doesn't have any initialize pixel data. So that's OK to construct an empty UMAT. But if we try to construct one with a pointer to pixel data, the compiler will say, well, there is no constructor without overload. That's an error. So the compiler will, OpenCV's constructed it so that the compiler will often catch out any misuse scenarios like this. One thing I like to do is to write my pixel data out to disk while debugging. But if you just used the umat.data member, the compiler will give you an error there as well. There is no publicly accessible data member, but OpenCV provide a way to convert a UMAT to a MAT, and that's called the getMat function. So that will, in effect, download the data from the GPU to the CPU, and then I can use my write method to write that out to disk. So when dealing with image processing algorithms, it's always handy to be able to debug them by drawing some annotations on the image. So right now I'll switch to an annotated version of this. So you should see a box around my face and with a little score. I'll get to that in a moment. So I'll just go through some of the code that draws that. After running DetectMultiscale, I'm then going to compose my output frame. So I get an empty output UYVY frame. And then I initialize it with my input data from earlier. Then the result of the face detection is a vector of rectangles. In this case, I've called it faces. So I loop through all those faces and I draw them on the output frame. OpenCV provides you a function called rectangle, which is very convenient for drawing these things. And one thing to remember here is that because the detections were done on this scaled down image, I need to scale those rectangle coordinates back up to the original 4K frame before I can draw them on the output. Now, often when you're processing and doing detection, you'll get spurious results. And what happens with DetectMultiscale is it will find more than one face in the image. So there'll be an image, a face detected around my face, but it might also be detecting some other face-like objects in the background or the foreground, or even in the shadows. So DetectMultiscale comes with another overload where I can pass in another result parameter. Here I've called it num detections, and it's a vector of int. And when more than one face is detected, each face will get a score. And that's what we're drawing underneath the face at the moment. There's a score under there of how many rectangles were, if you like, collapsed together to produce a face. So how many sort of subface objects were detected in this region, and that is a very good way of giving a score, like a confidence score of how face-like that rectangle is. So in the code, I use max element to find the element which had the highest score, and then standard distance to find the index, and then I'm going to create a rectangle called best face, which is a rectangle of the coordinates of that best index. And the final step in this composition is to take that best face, and we're going to extract the rectangle out and move it into the top left corner. So let's have a look at that on the output of the Ultra Studio. So green is highlighting the best face. If I have more spurious face detections, which you might see occasionally showing up, they'll get a score, but it's a low score. The green one is the best face, and then that gets pulled out and put into the top left corner of the image. The code for that involves taking that best face rectangle, scaling it back up into the original 4K dimensions of our output frame. Now, sometimes we need to clip it because a face might be detected on the edge of the frame and the coordinates for that rectangle might fall outside the frame. So we need to clip that to our output frame dimensions. And then a very convenient function, copy to, we can copy to the output frame that original rectangle, and our output coordinates will be the top left, 0, 0, and then the width and the height of the clipped rectangle. The final call there, schedule video frame, is a declink call, and that tells declink to take that output frame and schedule it into the SDI stream in the next position. So a couple of things to remember when you're doing live processing is to track objects rather than detection. So what I've been demonstrating here is detection. Every frame from the camera is being processed separately. The full face detection algorithms are running on the full frame, but a much smarter way to do it would be to take the original face's position, then remember the coordinates of that rectangle, and in the next frame, use a slightly larger bounding box to start your search, if you like, to narrow down the amount of data that needs to be processed. And this is often used when you want to detect more features. So you might use a scaled down image like I've done to find the face, and then you use that as your starting rectangle to look for eyes. So there's an eye detector that is available in OpenCV's installation, and that can be used to do eye tracking. Don't be tempted to iterate over pixels. So we saw earlier when I thought I was being smart, I created my own custom loop to iterate over pixels and cut out 2 steps or combine 2 steps into one, and that ended up being slower. OpenCV is almost always going to be faster. If you do have a custom processing step that you want to run on the image, OpenCV provides for each function, and you can give it your function object and it will execute that in parallel. Down conversion and subsampling your image is the most obvious way to speed up live processing, and you'll be surprised at how robust the detection algorithms are to significantly downscaled images. But perhaps the easiest way to take advantage of hardware acceleration is to use UMAT instead of MAT. So for more information, you can go to the Blackmagic Design developer website. There's also a software development forum, and Blackmagic also offer free developer support. Thank you for watching.